Your talk is going to be on extreme architecture performance.
Hmm.
And the architecture word itself is slightly scary, I guess. And when you add extreme on top of it, how does that sound?
Um, it sounds like a lot of fun. It sounds like something, yeah. One of the things that we have to deal with is everyone wants to be faster. Every
Yeah.
time that you build a new system, the performance is a consideration. It turns out there are typically two ways of adding performance to the system. One of them is to add a lot of micro optimizations.
Hmm.
You can using three things, you can try going really, really crazy deep in what you want to do in terms of the low level details of the code. But at the same time, a lot of people, I'm not sure what the term for that is, but they basically neglect or not even paying attention to what is the overall impact of architectural decisions.
Hmm.
A few years ago, we had to make a major rebuild of our project, and one of the things that we noticed is that when we shifted our thinking to how we build and how we design the system, the overall behavior was so much more different. And that led us to having far greater success in achieving our performance goals. And it's funny because we haven't actually, in many cases, done much,
Hmm.
but by here's a good example. Let's say that you're writing something that deals with IO, and
Okay.
IO is an extremely slow process. Well, you can build in caching and you can do all sorts of really crazy things. Or alternatively, you can go and look into how is the IO subsystems and the kernel and everything in the middle is working, and let's optimize everything for that. So, for example, if you're reading everything sequentially, then you have read-ahead features in the kernel. Okay, so let's see if I can design my underlying systems to operate on that assumptions. And suddenly you're getting orders of magnitude better performance.
Hmm.
And in the context of .NET, for example, uh, let's talk about allocation and the garbage collection. And it used to be the case that people assume that allocations are mostly free, and then you see processes running with 80% CPU utilization in GGC. And then you realize, okay, I can go and fix something and get six orders of magnitude difference in performance by maybe 15 lines of code of changing the way that you're doing things. That's absolutely
Right.
crazy.
Amazing, amazing. And I'm very excited about to know more. So I'm going to bring in your slide. Oren, all
Yeah,
right, stage is yours. Take it away.
thank you. So my name is Oren. I'm a Microsoft MVP for this 2007 also, a Twitter handle, and I'm here to talk about the process that we went in the RavenDB project. RavenDB started in 2008, and in 2014-15, around the time of .NET 3.5, we ran into a wall. It used to be a pretty typical web application in terms of the overall architecture, had a very rich client, and we basically couldn't get the right performance. When I mentioned that we had 80% CPU utilization in the GC, that was that application. Now, RavenDB is a document database. It does a lot of operations and it deals with a lot of data. So that was really, really painful. So we wanted to fix that. But I want you to look into something here. You see this is the timeline up to 2015. Every single release, every single one had performance improvements in there. Some of them were really incredible performance improvements, but we basically hit a wall. We couldn't do that anymore. So effectively, all of the code base was doing too much and too harshly. So we have to go back and figure out what we can do about that. Now, that was basically hitting the reset button. Now, there is a really good article by Joel Spolsky who talks about the absolute worst thing that you can do. So this is something that is really risky to do. In our case, it was the only option because the code base was too large to make a smaller incremental changes. It took it took 2.5 years, 3 years to actually complete that. Now, just to give you some idea, those were our goals. If you're going to do that, it has to be at least 10 times faster. It has to be able to run on cross-platform, but before we run it on Windows only. It has to have the same feature set, and one of the key aspects was that we wanted to build it with all of the lessons that we got from running in production for 5, 6 years. We also had a major mistake. We gave up on strict backward compatibility. Uh, in hindsight, we could have insisted on backward compatibility and it wouldn't have it too much. But the good thing about it that it allows us to make some significant modifications. Another really important consideration was that it had to be cross-platform. At the time, this was just when the DNX, if you remember what .NET Core was before that, it was just started, and we just look at that. It was compared to today, it was a horribly complicated mess, but we got it working. And then we started running very quickly, and now we're here. Uh, so here's the issue. There are two ways that you can be smart. You can be really Einstein level smart and do things, or you can be pretty stupid and get things faster. Now, it sounds silly when I'm saying that you can be stupid and make things faster, but it tells us that if you're going to really complicated solutions, sometimes you can get the performance out of them for certain scenarios. But the problem with doing that is that the level of complexity that you have to deal with is tremendous and it's compounding. Now, you don't have to be stupid. Select up, don't go with those sort of algorithms. They're not going to be helpful. But if you can keep your algorithm somewhere around here, you're good. But again, this is not something new. We have pretty much removed those sort of things uh, 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 from our system. So after we drop the stupid stuff, what remains? So I want to focus on some scenarios. And here is the first one, which is probably the most obvious one. Just routing a request. If you have a GET request, this is the API, this is this is the request that arrives on the network. This is what is translated to. So we want to take this and translate it to that. And you can see something really interesting here. I'm running a benchmark of 100 clients with 5,000 requests each, and you can see this guy, 85% CPU, out of which most of this is in the garbage collection. And those are numbers for 2016. So you can see this is when this returns nothing. So all we are testing is the cost of the framework. And you might be thinking about, okay, 15,000 requests, 20,000, 23,000 requests per second is an interesting number. Certainly, it looked like NantiFX of that time was significantly faster than SPNet, but that's so costly. Just to give you some idea, this is from Nancy. This is the faster version. And you can see something really interesting. You see here, this is an allocation. This is an allocation. Look at what's going on in here. So those things are things that would be costing us later because we have to allocate them. Here you can see we are allocating a dictionary. Here is another dictionary that we're allocating. We're using link. Now, link is a really nice system. It gives you very good clarity of code. It's horrible for performance. In our code base, we don't allow to use any link feature in the hotpath. In Rosing, for example, it's just not allowed to use link at all. Now, the problem here is that this is like having a payday loan. It gives you immediate gratification, the code is easy, but then you have to pay for that a lot afterward. So remember, we are now talking about something that is very, very specific. I want to route a request. So one of the most important behavior and most important things that you can get is if you can understand what limitations you can accept. And the more limitations you can have, the better you are. Why is that? And the answer is actually quite simple. If you're running with more limitations, that means that you have to do less. So, for example, when I'm building a routing system, I'm going to assume that the routes are ASCII only. I don't need to do Unicode routes. This is my routing. I'm going to make that happen. If I'm doing ASCII only, that gives me a tremendous number of optimization that I can use. I don't have to deal with all of the cost of Unicode. I can assume that there is one-time setup. There is a limited amount of routes to deal, so I can apply a lot of optimization on that. I can also say I'm not allowed to do any allocations for the routing. So let's see where it takes us. Here is something really, really simple. Look at the two numbers that we have here. What I'm doing here, I have this resource locator, which effectively is a dictionary. This is a dictionary using a ordinal ignore case option. So basically, this is me trying to do a case insensitive lookup between the case insensitive lookup between the expected routes and the route that I have from the user. And here is me optimizing that. Now, you might notice that the level of performance that we have here is drastically different. Just to give you some idea, here is the code that I have here. So when I'm calling try get value, the first thing that I'm going to do, I'm going to try to use that in the items. This is ordinal and this is ordinal ignore case. The difference in performance between those two is horrendous. So if I cannot find this thing, I'm going to look it up here. And this is actually really interesting code because this is actually a code data structure. This guy only happened once, and this is never mutated. But items may be mutated concurrently by different threads. Now, I don't want to have lock-in here, performance matters. So remember when I talked about limitation? I'm going to say, okay, I have a roughly fixed set of routes. I can optimize for that. The user calling me might be using a different casing from one client to the next, but they're also going to use the same one all the time. So I'm basically doing memorization. And I'm doing memorization, so and now I'm learning what is the new version of this key. And this is set here. And here I'm actually doing a RACI update. So if two threads are accessing this and modifying them, one of them will win and we have this new value here. And one of them would just get lost and the GC would collect that. So this is actually thread safe concurrent code with the cost that if we have actual racing here, we're doing a little bit of more allocation. But the next time that we hit it, then the race would be gone and this would resolve to steady state of no allocation and knowing already all of the paths that the user is using. And you can see that this can have major impact. Now, just to give you some numbers, this is, again, this is from 2016. This is how much it takes to route. And now we move to Nancy. And you can see that the difference is staggering. Now, Nancy is using a tray, and tray is the right feature here, but Nancy is doing a lot of allocation, or at least it did a lot of allocation in that code path. So now we're moving to this guy. And I want you to check, this is the difference in performance from the stock implementation. And that's less than one microseconds under the profile. Now we're going to take the same technique and apply it in a different location. Again, with RavenDB, all of our dates are in this specific format. Now, if we call data to string, that is a horrendously expensive operation. The toString have to parse the format, it has to do a whole bunch of computation, whatever. It also does a whole bunch of allocations. So that's too expensive. We rewrote it like this. And I want to show you the code. Here is the code for datetime formats. We accepted ticks. In here, all of this code is taken from actually the datetime format class, and this is do once breaking up into the parts of the dates. And now we are doing a whole bunch of really low level work. And you will notice that this actually doesn't do any allocation. This works on the raw memory directly. And here we are generating a single string. We are violating the assumption that a string is immutable. And we are now processing that data directly. Now, this gives me almost 5 times faster speed. This is really important. And again, these states doesn't these numbers doesn't tell the whole story because you have the allocation cost that you're paying for that later. Now, the problem here is that you can make those changes all the time, but eventually you hit the wall, and we need something better. We need the architectural difference itself. So here is a typical query. Give me this is the collection, here is a query, and do some projection from that. If I'm storing the data as JSON, you can see here all of the allocations that I'm making, and a 37 kilobyte JSON file may end up being half a megabyte when you deserialize that. But you know what is the biggest cost for us, which was absolutely insane for me to figure it out? Take a look. We're writing JSON. That's expensive. Where's the cost? This method. One, two, three, four, almost 40% of my time is spent writing escape string. A lot of my time is spent in managing allocations for disk. So we decided that instead of using the JSON format internally, we're still using the JSON format to read and write from the external, but internally inside of RavenDB, we have decided to build our own binary format. This is a format that we call bleedable because you can use it as is. We're using unmanaged memory, pointer arithmetic, all bunch of really low-level code. But the whole idea is that once we load the document, we have to do no parsing to access that. We don't have to create intermediate objects. And there are also a bunch of other things that we are learning as we go, but I don't think that we have time to go for that in here. And just to give you some idea, here is the difference in performance. This is the bleedable and this is JSON version. Now, that had some significant advantages. We don't pay the parsing cost every time that we read from the disk. We have the format that is optimal for a retrieval. We start learning the shape of our documents and use that. For that matter, we started taking ownership of memory. Instead of having just new all the time and allocate, we started creating a context. And the context was a major concept for us. It is used all over our code base. This is how you do allocation of both managed and unmanaged resources. And unmanaged resource for us is mostly unmanaged memory. That was a major architectural decision. A lot of the course that we had was allocations that we could predict the lifetime of. And if we can predict that safely, we should be managing that ourselves. Why? Because we have far better control and we can get it out of the GC. And if the GC can handle only the unexpected, the rare, the things that are complex to deal with, then I'm leaning on the GC for correctness and safety, but I'm able to get all of the benefit of manual memory management, of speed and predictability and all much of optimization that we can have. For example, we're using something called arena allocator. So every context has a buffer that is allocated to it. And every time that we need to allocate, we just bump a pointer. When we need to release that memory, we're not releasing individual values. We just drop the pointer back to its original location and we can move on from there. So the act of freeing all of the memory inside a particular context is setting off one value. You cannot beat that performance. It also meant that we had to move to a zero copy model. IO is super expensive. We are a database, that means that we are doing that all the time. We have to deal with IO pretty much everywhere, and we have users who are running on slow systems, they're running on the cloud where IO is at premium. So you have to do buffer caching, and you have to do a lot of that. Now, there's been multiple PhD dissertation doctorates on buffering in databases. This is really, really, really hard to do. But we realized that we can take advantage of the underlying system. So RavenDB would memory map the data and then allow the internal behavior of the system. So the kernel will decide what should be in memory and what not. That spare us the need to have our own buffering as well as the kernel buffering. It means that we are actually a much better neighbor in your system because the kernel has a global view. Now, we still need a lot of optimizations, but now instead of building those optimizations, we are going to be able to say, hey, let's figure out what patterns the kernel already recognize. For example, read ahead, sequential reads, sequential writes, those sort of things, and let's change our behavior to follow the way that the kernel would optimize, and suddenly you get really good performance. So just to give you some idea, in my system, I need to render a document to send a document to the user. I look up where it's located on the disk. I get a pointer. In most cases, that pointer, almost cases, that's a memory map file. In most cases, it's actually in memory. If this is something that happened once or twice, no worries, the kernel will read it to memory and then evict it. If it's hot, we get it for free. The kernel will make sure that this is returned in memory. And now we can operate over the raw memory bytes with no additional work. So I'm using async IO in Kestrel. So I'm going to the storage, give me this particular document. The storage give me this pointer. And then I can hand that pointer to the IO system, to the network, write it to the user. And we're done. We're done. There is no need to do caching. There is a lot of stuff that actually isn't even there. And as I mentioned, a lot of that is about understanding the environment. And the idea here is that we really wanted to make sure that, okay, how is the GC going to work? How is the kernel, the IO, all of those sort of things? In the terms of the GC, if you can avoid allocations, that's awesome. But in many cases, you can't. So, okay, I have very long-lived allocations. That's great. They go on Gen 2, they're rarely allocated. Very short-lived, okay, many cases we can optimize them significantly. But there are several unfortunately common patterns of holding an object for a relatively short amount of time, enough for it to get promoted, and then discarding that. If you have a cache that is almost full, for example, then what it turns out is that the cache is going to be poisoning the GC. It's going to keep the objects in memory just long enough for them to be promoted, but not long enough to actually make proper utilization of that, which means that you actually have to consider some pieces of your code as almost hostile because of the interaction between the caching system, memory pressure, and the GC. Uh, Memory ownership and taking manual memory management in a managed application was another major consideration. Now, a key observation here is that we don't have to do either or. It's not only managed memory, only unmanaged memory. We're able to say, okay, in some cases I can do that optimally. So this is where I'm working. This is where I'm doing all of the easy stuff myself. And that's 80, 90% of the cases. That gives us a huge performance boost. That means that from the GC perspective, there is a lot of memory that it doesn't manage. It doesn't have to track those object graphs. And that means that we get far better performance. Notice that those sort of architectural decisions are one of the reasons that we have to almost build it from scratch because they are really, really pervasive. So this is something that you don't just start applying, although you can start using that in certain cases quite easily. And a lot of that, and again, this is, I think, one of the best case scenarios. A lot of that is not about writing more code. A lot of that is understanding what's going on in the entire stack and then applying yourself and selecting the appropriate processes that will take advantage of that. And suddenly you have tremendous benefits, but you haven't written the code. And in many cases, to reap those benefits, the analysis are in some cases trying really hard to figure out how to make things easier for you. And they have all sorts of heuristics. And if I play to those heuristics, suddenly everything is just flowing really, really nicely. Uh, Another thing that I want to talk about is that those changes that we looked at, I feel that they weren't just in our team that did that. They were almost in across the entire industry. And suddenly we started seeing, especially when the project became open source and and it started accepting contributions, then a lot of the low-hanging fruits, oh, I'm doing an allocation here and I can save that, but no one is going to do the work on actually doing that because there is a limitation to the team size. Once we had .NET Core as open source and accepting external contributions, people starting to chip away on that. And in many cases, those are very, very specific changes. And every one of them adds, 1% to your performance, those sort of things. The key here is that this create this avalanche effect. And you can see here, I put the metrics for when we move from .NET Core to something to 3.1. And it's very, very clear when that happened. Both the total CPU amount and the behavior it just dropped significantly. And this is literally we had a release where changed the we just changed the version of .NET that we're running on. That's it. I'm very happy to have that. Hey, I got almost 50% performance improvement from my perspective, almost no cost. And we've continued to see that over and over again in the .NET community. This is something I'm very happy about. And that's it. Now, if you have any questions, I'll be very happy to answer them.
Yeah, Oren, that was a very, very insightful session. I mean, giving an idea about the TNX to .NET Core to .NET, and specifically the last slide, which you showed about the 3.1 migration and the performance boost there. It's really, really nice to see that, especially in something like where you're using RavenDB, right? Uh, yeah, awesome. Okay, so I am trying to see if there are any more questions. So as of now, I don't see any. So Oren, I will let you go. Thank you so much for sharing these insights, and I'll see you next time.
Thank you for having me. Goodbye.
Thank you.